Hello and welcome in to the content video for lesson 7 for Precalculus 1. In this lesson, in this content video, we're going to be talking about systems of equations. And we're going to be looking at three types specifically. We're going to be looking at systems of two equations, where we have just an x and y variable. We'll be looking at systems of multiple variables. So we're just going to look at three, but essentially you could have a system that has, a ton of variables in it. And then lastly, we're going to look at nonlinear systems. And so let me share my document camera here with you guys. All right, so to begin, I'm going to look at the systems of two variables as well as the non-linear systems. And the reason being is that we essentially solve them both in one of two ways generally. We either solve them by substitution, yep, or elimination. Now, sometimes substitution is easier. Other times, if we don't have one as the coefficient for some of the variables, substitution can become messy because we'll get a bunch of different fractions. And so what we would do in that case is elimination. And so, for example, like a very basic example, let's say that I have a system that, say y equals 2x. And again, I know I normally don't do examples on these content videos, but that's going to be the easiest way to sort of illustrate these two methods. And to be honest, you guys probably know these anyways. If you have taken an SAT, ACT, if you had high school algebra, I'm sure that you did some of this stuff, and that's fine. Hopefully, it's just a refresher for you guys. And so maybe we have one system that says y equals 2x, and the other says y equals x minus 5. And so in this situation, substitution is easy because we're saying that y is 2x, so we can just plug that into here and then solve for my variable x and then plug it back in for y. So for example, if I was to substitute this, y is equal to 2x, I end up with just 2x equals 5. And then again, from a time standpoint and a illustrative standpoint, you probably can, so hopefully you can solve this. We've done linear equations. That's what you have at this point. You're going to get what if we subtract x? Like I said, we'll work it out. We get x equals -5. Now that we have -5, we can plug that back into either one of these equations to get our value for y. And the nice thing about these, if this is on a test, if this is on your mastery sets and you have to get it right, you can always check your answer because whatever you get for your values of y and x, plug it into both systems. And as long as it makes a true statement for both equations, then you know it's correct. Now, sometimes substitution might not work because it'll give us a really messy values. And so maybe we have something like 2x plus 3y is 4, and 3x minus, let's say 5y equals, I don't know, let's say 10. And these might not work out. I'm just making these up off the top of my head. But the idea being that I can't really solve this equation for x and y and get nice numbers. I can't solve the second equation for x or y and get nice numbers. I could divide by this -5. That'll work with the 10, but then I get a fraction with the 3. And so what we want to do, so substitution method, we're just plugging one equation into the other and solving it. With elimination method, My goal is to get opposite coefficients for one set of variables. And so let's just look at this x variable here. If I want to get opposite coefficients, I can do what? I could multiply this first row by -3. And as long as I multiply every term in this equation by -3, I haven't really changed the equation. I just changed how it looks. So I get what? -6x minus 9y equals -12. And then if I want these to be opposite, I need this to be what? A 6x. That way, when I add down, the x variable is eliminated. So I have to do what? I have to multiply this row by 2. So I got 2 times 3x is 6x. 2 times -5y is minus 10y. And 2 times 10 is 20. And now we add down, so -6x plus 6x, they cancel out, which is what I want. Add down, so -9 minus 10 is -19y. Add down, 20 minus 12 is 8. So again, you can see it's messy answers because I was just making this up in my head. But the idea that I want you to get is that we're matching up, and you could have done it with the y values. Maybe this was a 2 and this is a 4. And it's like, oh, well, I can just eliminate that easy enough because I only have to multiply one row by 2. That's okay as well. The goal is just to get either the x variables or the y variables to be the opposite of each other. So when we add down, we get just one variable remaining with a constant value. Now, we have two special cases for this. When we do substitution or elimination, if we get a result with a number on one side is equal to 0, so let's say I did substitution and I solved it and I get something like, so let's say i.e. 3x, no, sorry. Let's say the variables cancel each other out. So I just end up getting a number like 3 equals 0, maybe. Well, that's not true, right? Because 3 can never equal 0. So when I get some number is equal to 0, and I should say some number that's not 0 is equal to 0, then this has no solution. If I do substitution or elimination and I get 0 equals 0, what this means is I can pick any values for x and y in a certain combination, and it's always going to make that system true. And therefore, what it means is I have an infinite number of solutions. Oops, infinite. I can spell here. Sorry, infinite number of solutions. And again, we're not going to really look and spend too much time on that in these videos. I'm not even going to give you any examples of those in the example videos. Yes, I just want you to know that it exists, that you could technically get no solution or infinite solution. But for the purposes of this class, I want to make sure that you can actually solve these systems and get one unique solution. And so therefore, you will get something like we had up above here, x equals -5, plug it in to solve for y, or -19y is 8, solve for y, plug it back into either of these equations to get x. So that's when we have a system of two linear equations. Now, all of that same information holds true for systems of non-linear equations. So we know from things we've been doing already this class, nonlinear means what? It means that we have one or more variables, in this case, that aren't to the first power. So maybe we have an x squared, maybe we have a y squared, maybe we have both. That would be a system of nonlinear equations. And again, just as an example, what it would look like, maybe I have y equals x squared, and then I have y equals x, I don't know, plus 2, something like that. And so we have we have the option, we could do what? We can do substitution. Once again, just plug in this x squared. Now we have a quadratic equation, solve for x. We potentially are going to get more than one answer now. So before we had just x equals -5 and then plug it in to get whatever our value of y is. But now, because the system is nonlinear, I could have multiple variables or multiple answers for x. I could have multiple answers for y. I have to take all of those into consideration. So actually, let me work this one just to show you what I mean by that. So if I do substitution and I plug this in, I get x squared equals x plus 2. So if I subtract x and subtract 2, I get x squared minus x minus 2 is 0. So now we have a quadratic equation. We can factor and use zero property rule. So I get x and x minus 2 plus 1. So x minus 2 is 0, x plus 1 is 0. So x is 2 and x is equal to 1. So I have two possible values for x here that I could use to make this system true in both cases. So then what I have to do to find the remaining answers is first, when x equals 2. So when x equals 2, plug it into either of these equations. So if I use the first one, I get y is equal to x, which in this case is 2, so 2 squared. So y equals 4. And you can see even if you plugged it in the other equation, y is equal to 2 plus 2, which is still 4. So one solution I have is x is 2, y is 4. But I also have this guy here. What about when x is equal to 1? Well, when x equals 1, I get y equals, wait, what did I do here? Oh, -1, sorry. X plus 1 is 0, so x is -1. So you guys are all probably screaming at me, no, no, it's -1, -1. Well, that's how we know, right? Because it should work in both of these equations here. So when we figure out our value for y when x is -1, again, I get y is equal to x, -1 squared, which is +1. And even if I plugged it in here, if I plug in x, -1, -1 plus 2 is 1, so y is still 1. So I have another solution of -1, +1. So I actually get two solutions for this system. That's using substitution. We can also do elimination method. If we have maybe two equations that have an x squared term, we could get rid of the x squared term, solve for the y variable, plug it back in to find out all our values for x. So that is also another option. So that's system of two linear equations, system of two nonlinear equations. Now, what about when we have a system of multiple variables, so more than two? So I'm going to give you a lot of terms here. So if you look into the book, if you have other instructors, if you watch other videos on the internet or, AI, something like that, and you're solving systems of multiple variables, you might hear terms like reduced echelon form, reduced row echelon form, Gaussian elimination, Gauss-Jordan elimination. These are all methods to do what we're going to be doing is a matrix. So these are methods of simplifying a matrix to solve these systems of multiple variables. Again, for the purpose of this class, I want to keep it simple. I want to keep it concise. I want to make it as feasible for you guys to figure out how to do these problems without adding more confusion to the mix. So the first thing that we are going to use anyways for this is what is called an augmented matrix. And so what an augmented matrix does is it basically removes the variables. So when we were doing system of two equations, whether it was linear or nonlinear equations, we had the x's and y's throughout the whole process, solving for x, solving for y, etc. But once we start getting, say, three variables, x, y, and z, it can get really messy if we try to keep those variables within the solution. So an augmented matrix, it takes some, so let's say we have like 6x minus 2y minus z is 4, and then x plus 3z is 1, and 7y plus z is 5. An augmented matrix takes all the variable pieces. So from this first one, we have 6, and like I said, I get rid of the variables. So I have 6, and what's the coefficients? Minus 2, minus 1, and then I need this constant over here, the 4. So all I'm doing is taking this 6, putting it here, taking the minus 2, taking the minus 1, and then taking the 4. I do that again for this second row, and I have 1x, so that's a 1. There's no y variable, so that's a 0. Plus 3z, so that's a plus 3 there. And then a 1 is my constant. And again, we put these brackets on both sides. We're creating this matrix here. And for the last equation, there is no x term, so that's 0. 7 is the coefficient of y. 1 is the coefficient of z, and then the 5. And so essentially all this does is say this first column is my x variables. Second column is the y. Third column is the z. And this last column is the constants on the right side of the equations. All right, so if you're in my class, you have that process, what do I call it, solution process guide or something like that. And it will tell you how to go about what our goals are, what our methodology is to try to make these as simple as possible. And so what we are going to do is I want to try to build a matrix that has the following characteristics. So my goal here is going to be to get one row with 1 0 in the variable columns, and then to get one row with 2 zeros in the variable column. And what I want is to have 2 zeros on top of each other or in line with each other. And we'll see why here in a second. And to do this, what I want here, so first, ideally, I want a 1 in the upper left. because this will make my math a lot easier. So if I was looking at this, I would have a 1 up here. And then once I do that, I'm going to do the following 3 steps. I'm going to use row 1 on row 2 to get a new row 2. Use row 1 on row 3 to get a new row 3. And then lastly, use the new row 2 that I made on the new row 3 that I made to get a final row 3. And by doing that, I ideally want to have a 0, or my goal anyways, would be to get a 0 in this bottom left-hand corner. So here I'm going to have some other numbers and then a constant, and then some other numbers and a constant, and some number and a constant. And so the reason that I want to get this to happen is it because what? Now this last row, remember, this is my X column, Y column, Z. Oh, so maybe I should just put like number signs here instead, or number hashtags. So I have all these different numbers. It could end up whatever. And then these different constants, say constant 1, constant 2, constant 3. Because this last row, I can now do what? I can convert it back to an equation with variables, because it's whatever this number is times z is equal to this constant. And so to do this row 1 and row 2 and row 3, I have 3 elementary row operations that I can perform. So the first one, whoops, that up for you. So the first thing I can do is I can switch any 2 rows. So like I said, ideally, I want a 1 in the upper left. Well, maybe when I was given the equation, so let me go back to here. Where's my paper here? So maybe when I was given the problem, this is what I was given. But I didn't start with a 1 in the upper left. I have what? I have a 6. But I could switch these 2 rows if I want. Why? Because these rows are just a representation of these 3 equations. It just so happened that this equation was written second, but there's no reason this equation couldn't have been written first, so I can just switch these 2 rows if I want. So the top row would be 1, 0, 3, 1, and the second row would be 6, -2, -1, 4. So that's perfectly fine to do. I can switch any 2 rows. The second thing I can do is I can multiply any row by a non-zero constant. So let's say that the top row was, I'll make it easy for us, 2, 4, 6, 8. Well, those are all divisible by 2, right? So I can multiply that row by a non-zero constant, in this case, 1/2. So I multiply 2 by a half, I get 1. 4 by a half, 2. 6 by a half, 3. 8 by a half, 4. So I can multiply any row by a non-zero constant, and that's acceptable as well. And then lastly, and this is where all of this comes in, use row 1, use row 1, use row 2, is I can add the multiple of one row to another. And so using those row operations, ideally, I get to a point that my matrix looks like this. So I have one row that has 1, 0 in the columns, the variable columns. I have one row that has 2 zeros in the variable columns, and I have 1 0 above another. Once I get to that point, and the reason I'm doing that, and again, we're not going to worry about Gauss-Jordan. We're not going to worry about reduced row echelon form. I'm not going to worry about any of that. Instead, as soon as I get that scenario, and I'm going to be blunt here, get the hell out of the matrix. So excuse my French there, but most people struggle with these kind of problems because they get confused by the matrix. What am I supposed to be doing? What numbers can I use? What do I do with one row to the other? So the quicker we can get out of the matrix, the better for us. And so that's what we are going to do. We are going to get out of that matrix as soon as possible. So again, I know I don't normally show examples on these content videos, but I'm going to show you one here going through these different things that I just showed you. So let's say, example, let's say I want to solve the system x minus y plus is 3z is 4, x plus 2y minus 2z is 10, and 3x minus y plus 5z is 14. So first things first, write our augmented matrix. So we have what? 1, negative 1, 3, 4. Second row, 1, 2, negative 2, 10. Third row, 3, negative 1, 5, 14. So with these systems of multiple variables, I caution you, I beg you to be careful with your numbers, your math, your work, your signs. Because if at one point in this entire process you mess up one bit of arithmetic or mess up one sign, the whole thing is done. You have no chance of getting it correct. So before you even start, I would double check that you wrote the matrix correctly. 1, negative 1, 3, 4, that's fine. 1, 2, negative 2, 10, that's fine. 3, negative 1, 5, 14, okay, that's fine. So now, ideally, I want a 1 in the upper left. I have that, that's great. So I'm going to leave the first row. And I'm going to do what? I'm going to do row 1 times something plus row 2 to give me a new row 2. So remember how I said row 1 with row 2 to get a new row 2? That's what we're talking about here. So what do I need to multiply row 1 by that when I add it to row 2, I get a 0? Because I want to get a 0 here, right? Uh-oh, pen is dead. Let's see. Let's go with this one, the blue pen. I don't know if it'll show up as blue, but we'll try it. Yeah, a little bit. So I have to do what? I have to multiply 1 times negative 1 to get a 0 here. So I do, and I'm going to give myself a little note here, minus 1. So negative 1 times 1 is negative 1, plus 1 is a 0. Negative 1 times negative 1 is plus 1. Plus 2 gives me a 3. Negative 1 times 3 is negative 3. Minus 2 is minus 5. And negative 1 times 4 is negative 4. Plus 10 is 6. So we get for the second row, the new second row, 0, 3, negative 5, negative 6. Now we're going to do the same thing again, but now we're doing row 1 times something plus row 3 to give me a new row 3. So if I want to get a 0 down here in the bottom corner, what do I have to multiply 1 by to get, when I add it to 3, I get a 0? Well, that's going to be what? -3. So -3 times 1 is -3 plus 3 is 0. -3 times -1 is +3. 3 minus 1 is 2. -3 times 3 is -9. Plus 5 is -4. And then -3 times 4 is -12. Plus 14 is 2. So that's the first matrix I get from, whoops, oh, and this was times -3. So that's the first matrix I get from row 1 on row 2, row 1 on row 3. Now, I want to use row 2 with row 3 to try to get another 0, but you can see these numbers aren't very nice. I can't do I mean, I could do 3 times -2/3, but then I get a big mess over here. But if we look at this last row, it's what? It's all factors of 2. So I could actually do row 3 divided by 2. And when I do that, I get what? So 1, -1, 3, 4, that doesn't change. 0, 3, -5, 6, that doesn't change. But divide all these by 2, I get 0, 1, -2, and 1. Whoops, sorry, let me move that up. And now, because again, if I can use a 1, it makes my math a lot easier. I'm going to switch row 2 and row 3. So let me move that up here. So when I do that, I get what? Well, 1 stays the same. Switch these two. So now I get 0, 1, -2, 1. And then the bottom is 0, 3, -5, 6. And why did I do that? Well, again, I want to get a 0 down here so that I get a 0 is in this whole bottom corner. And it's a lot easier with this being a 1. Because now I can do what? Row 2 times -3 plus row 3 gives me my last row 3 that I'll end up with. Again, let's put our little note there. So 1 stays the same, 2 stays the same. And we have what? -3 times 0 is 0 plus 0 is 0. Once you get a 0, you should not put a number back in there because now you're defeating all the work you've done. So once you have a 0, it should stay a 0. And that's why we're trying to get zeros on top of each other. So now -3 times 1 is -3 plus 3. There's my second 0. -3 times -2 is 6. Minus 5 is 1. And -3 times 1 is -3 plus 6 is +3. So we got what we want, right? A 1 in the upper left, zeros in the bottom corner. One row has a 0 in the variable column. The other row has a 0 in 2 of the variable columns with a 0 on top of each other. And now what do we say? Get the hell out of the matrix. Why? Because this bottom row, this is my X column, Y column, Z. So I can rewrite this as what? 1Z is equal to the constant, or just what? Z is equal to 3. And now, just like we do with systems of 2 equations, whether it's linear or nonlinear, we're going to back substitute. We're going to put the number back into the equations. And so which equation am I going to use? I'm going to use this one, the second one that has a 0 in it, because this means what? This second row means y minus 2z is 1. And we just found out z is 3, so I get y minus 2 times 3 is 1. So y minus 6 is 1. Add 6 to both sides, tells me that y is equal to 7. And now that I have that, I can use the first row, which is x minus y plus 3z is 4. Plug in my values for y and z. So x minus y, which is 7, plus 3 times z, which is 3, is equal to 4. So x minus 7 plus 9 is 4. X plus 2 is 4. So subtract 2 from both sides tells me that x is equal to 2. So your answer for this, written as a ordered triple, is called. So normally we like to have x and y coordinates. Now we have x, y, z. So my x is 2, y is 7, z is 3. If you want to know if this is correct, if this is on a test, plug these values back in to the original equations, and you just have to check it in 2, because if it works in 2, it's going to work in the third one. It has to. So plug 273 into this first equation, plug 273 into the second equation, and if they both work out, you know that it's right. All right, so kind of a lengthy video there. I know it's longer than the normal content videos, but I did want to sort of go through this example of these systems of multiple variables just to make sure you understand the steps behind it. And in the example video, I'll do another one again just to show you, to make sure you really have a grasp on what's going on. So that is it for this video. Come on back and I will see you guys in the lesson 7 example video.